Welcome to our lecture on discrete probability distributions, Chapter 5 in your text. So, a random variable is a function that assigns a numerical value to each sample point. Discrete random variables are described using the probability mass function, or PMF. So, the probability of an individual x is denoted as P of x, big X equaling little x. Big X is the variable, little x is the outcome. They are often described using the cumulative distribution function, the CDF. So big F of x is the probability that the random variable x is less than or equal to some individual x. A discrete probability distribution can be viewed in a table, algebra, or graphical format. Take the number of houses sold by our realtor in a month. I could list it in this table, or in a function, or in a graphical format. We can also construct numerical summaries of random variables. The mean or expected value of a discrete random variable is, so first of all, let's talk about notation. So mu is the population mean. You should remember that from your previous stats class. E of x with a capital E is read expected value. So that E of x stands for expected value. An expected value of a random variable is synonymous with the population mean. Sometimes it makes more sense to talk about it as an expected value, like if you are running a casino and you need to figure out the average loss on a game. You usually think about that in terms of how much do I expect to lose on this game. All right, so it's just another way of thinking about the population mean. So the population mean or expected value of a discrete random variable is the sum, so this is big sigma right here, of each individual x times its probability and add all those up. The population variance for a discrete random variable is very similar to the sample standard deviation or sample variance formula, and that is the sum of each individual x minus the mean squared weighted by the probability of seeing that deviation. So those are your formulas for discrete distributions. For example, if we have the distribution of the number of dental visits in a semester for college students, pretend like you can only go 0 once or twice, we're going to assign a probability of 0.45 for 0 visits, 0.3 for 1 visit, and 0.25 for 2 visits. So let's calculate the expected number of visits in a semester. And that would be taking each possible value times its probability. So 0 times 0.45 plus 1 times 0.3 plus 2 times 0.5. Work that out on your calculator and it comes out to be 0.8 visits. Make sure you make a note that we do not round these. So do not round, just so it can be a possible value in the distribution, because this is a theoretical balancing point in the distribution. Remember, a mean we're thinking of as a balancing point. So that's just how many visits we expect on average if we were to sample lots and lots of college students and average their number of visits. And then the population variance is calculated just applying the formula. We take 0 times the mean, 0.8, squared, times the probability of seeing a 0, 0.45, plus 1 minus the mean of 0.8 squared times the probability of seeing a 1, which is 0.3, etc., and we get 0.66 visits squared. And so to calculate the population's standard deviation, sigma, just take the positive square root of that to get 0.81 visits. Don't forget your units on these. All right, so we're going to talk about two specific discrete distributions. The first one is the binomial distribution, and the next one's going to be Poisson. But for now, the binomial experiment. This is where we have n identical trials where each trial has only 2 possible outcomes, which we'll call a success or a failure. And the probability of a success is the same, p, for every single trial. And the trials are independent. These individual trials are called Bernoulli trials. So we've got this formula. The probability of j successes in n trials is n choose j times p to the j power times 1 minus p to the n minus j, where n choose j is n factorial, that's that n exclamation point, which is n times n minus 1 times n minus 2 all the way down to 1, divided by j factorial times n minus j factorial, and we define 0 factorial to be 1. Now, You probably hand calculated some of these guys in your previous stats class. Again, this stats class is heavy emphasis on the applied. We're going to be computing binomial probabilities using R. That's the way we do it in practice, and that's the way you guys are going to do it. So here's an example of the way a binomial distribution might look. This one has n equals 10 independent trials, and a probability of success is 0.2. So you can see that the mass is located right here around 2, because you can imagine that we would expect 2 successes out of 10 trials if the probability of a success is 0.2. All right, so we could calculate the mean and variance of this discrete random variable using our old formula, right? The ones you just learned. Like the mean would be 0 times the probability of seeing a 0, plus 1 times the probability of seeing a 1, plus 2 times the probability of seeing a 2, all the way up through 10. However, there's a shortcut when your discrete random variable is the very special one called the binomial. And that is the mean of a binomial random variable collapses to be n times p. And the variance ends up being n times p times 1 minus p. And of course, if you want the population standard deviation, then you just take the square root of n times p times 1 minus p. Okay, so as promised, R is going to calculate binomial probabilities for us. So let's pay attention to these functions. In R, for our probability distributions, we're going to have our D functions and our P functions. So the binomial ones are D binom and P binom. All right, the D functions in R calculate the probability of being exactly equal to a single value. So if you give the D binom function your value that you want to calculate the probability of being equal to, comma, your sample size, comma, your probability of a success, it's going to give you the probability of being exactly equal to that number j. The P functions in R are the cumulative distribution functions. This gives you the probability that your binomial random variable is less than or equal to a specific value j. So P binom of j, comma, n, comma, p gives you the probability of being less than or equal. So let's jump right in and do some examples so we can get a handle on this. So consider a shipment with 2% defectives, and the chance of being defective for any 2 components does not change depending upon whether the other is defective. Find the probability of having exactly 1 defective out of 10. Now, I'm going to recommend strongly that you write the words into a probability statement first when you're attacking these problems. So how do we write these words in a probability statement? Well, we want to find the probability of this binomial random variable being equal to 1 out of 10. So that's the probability y equals 1. All right, that's a good start. Now that we know we want to find the probability of being equal to, we have an R function for that. Specifically, that's our D binom function. So we're going to use D binom of our number of interest, 1, our sample size, 10, and our probability of a success, which is 0.02. 2% defectives, 0.02 is our probability. And that ends up being 0.1667496. If I asked you to round that to 4 places, we just look at that 4th place, take a look at the 5th one. If it's 5 or higher, we bump that 4th place up. If not, we keep it the same, so it would round to 0.1667. Okay, so we've got 1 binomial probability under our belt. Now let's find the expected number of defectives in the shipment. Well, remember that shortcut formula when we have a binomial distribution for the expected value, that's just n times p. So what's n here? It was 10, and what's our p? 0.02, and that ends up being 0.2 defectives. Now, make sure that you do not round this. Remember, we don't round means and standard deviations just so that there'll be a number in the distribution. It's a theoretical balancing point in the distribution. So remember, if you come up with something other than a whole number, do not round it to be a whole number. Okay, so now let's try a different example with lots of different scenarios. When I go through this one, it's going to go through all the different scenarios that you can possibly reach when you're calculating probabilities with a discrete random variable. So a local jazz club, 40% of performers go on to release an album. 10 performers are randomly selected. What's the expected number that will release an album? Well, again, we're in the binomial distribution. We've got n equals 10, a probability of success of 0.4, and we can either just have a success or a failure on each trial. So we can compute the binomial mean with our very special formula, n times p. So the expected number of album releasers is going to be n times p. We just said that n was 10 and p was 0.4, and so we're going to expect 4 performers to release an album. Now make sure you remember, we happen to get a whole number here, but if we didn't, we wouldn't round it. All right, so now let's find the probability that exactly 2 of them release an album. So the first step is to write this words into a probability statement. So exactly 2 is the probability that our random variable equals 2. And again, we've got a formula for that directly, a function directly in R, and that's the d binom function for exactly equal. So we want d binom of our number of interest 2, comma our sample size 10, comma our probability of success 0.4, and it's going to give you 0.1209. So you literally just type in at your cursor in R, d binom with the parentheses 2, comma 10, comma 0.4, and your parentheses. All right, what's the probability that 9 or fewer release an album? All right, so first let's write this words into a probability statement. 9 or fewer means 9 or less. It means less than or equal to 9. So make sure you know that's not a strict inequality. 9 or fewer could include 9. So probability x is less than or equal to 9. All right, well, we have a function for this in R. That's our p binom function. It will give us the probability of being less than or equal to. So we want p binom of our number of interest 9, comma n is 10, comma p is 0.4, and it gives us 0.9999. Very good. Okay, so now let's compute the probability that 3 or more release an album. So once again, let's take the words and write them in a probability statement. Probability of 3 or more is the probability that x is greater than or equal to 3. It could include 3 because 3 or more means it could possibly include 3. Well, we don't have an R function for this, right? We only have a function for exactly equal to a number or less than or equal to a number. But hey, we can use our complement rule. So what's the complement of being bigger than or equal to 3? It's being less than or equal to 2. So we can use 1 minus the probability that x is less than or equal to 2 to compute the probability that x is greater than or equal to 3. All right, so to picture this, just imagine that your possible outcomes are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? Because 10's our number of individuals that we're checking, and you can go all the way down to 0. So the probability of being, so all of these added up, the probabilities would be equal to 1, right? Because that's everything in the possible sample space. So if we want the probability of being 3 or bigger, the complement of that is 2 or less. So we can just use 1 minus the probability of being less than or equal to 2. All right, so remember that little trick because we'll be using it again. And now we have directly a function for the probability x is less than or equal to 2, namely our p binom function. So 1 minus p binom of 2, comma 10, comma 0.4 gives us 0.8327. Very good. So let's try another one. What's the probability that more than 3 but less than 8 release an album? So again, first step is taking the words and turning them into a probability statement. So I'm usually just write down, I'll just write down 3 less than y less than 8, and then decide whether these are strict or non-strict inequalities. Do we have a strict or non-strict inequality here? More than 3 is strict. Less than 8 is strict. So we're not going to put the or equal to sign on them. So we have this inequality. So how are we going to turn this into a probability statement that's going to allow us to use R to calculate these probabilities? Because remember, we only have the equal to function d binom or the less than or equal to p binom. All right, so first I'm going to change both of these strict inequalities into non-strict inequalities. So if x is less than 8, what's it less than or equal to? 7. If it's more than 3, what is it more than or equal to? 4. So I'm going to change my probability statement to being the probability that 4 is less than or equal to x is less than or equal to 7. So I would highly recommend just following whatever method works for you, follow it every time. That way you won't make mistakes. So the way that I'm going to teach it to you is starting with changing the words to a probability statement and then change your probability statement into non-strict inequalities with those or equal to signs on them. Very good. Now, how do I compute this? If I use p binom of 7, what's that going to give me in R? That's going to give me 7 or 6 or 5 or 4 or 3 or 2 or 1 or 0. But I only want 7 or 6 or 5 or 4. So if I want to keep 4 through 7, I could do p binom of 7 and then subtract p binom of 3. I want to keep 4 on up, so I throw away 3 on down. And that's the trick that we're going to use to get these kind of probabilities. P binom of 7 gives me 7 all the way down to 0. And then I only want to keep 7 on down to 4, so I throw away 3 on down to 0. And when you punch that into R, you get 0.6054. Very good. So that's all the scenarios that I could possibly hit you with when you're computing these kind of probabilities. Make sure that you practice these with your Check Your Knowledge questions and going through these notes and doing the practice homework that I've posted, because it can be a little bit tricky, but once you get the hang of it, if you follow the little steps, you will start to not make mistakes and it'll become more natural. All right, so now we're going to learn the other discrete distribution called the Poisson distribution. So a Poisson process is let x be the number of events occurring during an interval of fixed length t. X is Poisson if only one event can occur at a particular point. Events occurring in one range are independent of events occurring in other ranges. And the expected number of events during any such interval is a constant mu, which we're going to call lambda. So this is the function for computing binomial probabilities. Mu to the x, e to the negative mu, divided by x factorial, where mu is lambda, and it happens that the variance is also lambda. And of course, this is for x equals 0, 1, things you can count because it's number of events. But again, we're going to use R to calculate our probabilities for us. And once again, the D function is going to give us the probability of being exactly equal to a number, and the P function is going to give us the probability of being less than or equal to a number. So the Poisson functions in R take your J, your number of interest, comma, your lambda, your mean. All right, so let's start right away with an example. So the projector bulbs in the lecture halls on campus that you use when you're watching us project something onto a screen at the front of a lecture hall are actually very expensive. They're several $100s a piece. So we need to keep extra ones on hand so that we have projectors that work, but we don't want to keep too many extra on hand because they're extremely expensive. So a projector bulb used in a classroom fails on average once every 500 hours, and the room gets approximately 900 hours of use in the academic year. So how many replacements are we going to need on average? Well, think about it. If one fails on average once every 500 hours, how many will we need in 1,000 hours? We would just need 2, right? So you can compute your expected number by taking the number of hours divided by 500. So if we need 1 per every 500 hours, we're going to need 1.8 for every 900 hours. So 900 divided by 500. Notice that this 1.8 is our lambda. That's our expected value. All right, so let's compute the chance we'll make it through needing no replacements. So once again, let's take the words and turn it into a probability statement. That's the probability that our random variable equals 0. And we have a function for that. We've got our D function in R. So D Poisson of our number of interest 0, comma our lambda of 1.8 gives us 0.1653. Very good. What's the chance that we need more than 2 replacements? Once again, take the words and turn it into a probability statement. So that's the probability that x is bigger than 2. More than 2 is bigger than 2, a strict inequality. And again, I'm going to suggest that you turn this into a non-strict inequality. More than 2 is more than or equal to 3. So now I can change this into a probability statement that we have a function for, namely the p Poisson, which will compute less than or equal. Well, what's the complement of being bigger than or equal to 3? That's going to be less than or equal to 2. So we're going to use our complement rule again, 1 minus the probability that x is less than or equal to 2. And that we have a function for, 1 minus p Poisson with 2 as our number of interest, comma 1.8. Notice the p because of our less than or equal to sign. And that gives us 0.2694.